Yeah, at first glance, it appears to be a bit off topic compared to other presentations. So I'm here to talk about this oceanographic instrument which we have developed during the Nautilus project, which is a European project, Horizon 2020. It's an ongoing project, and we are currently in its third year. We still have 2 years to go, and currently we are beyond testing phases. So what I will be presenting are some preliminary test results and so forth. So before I would start, just a quick consideration of the title. Perhaps the correct title, as it seemed at the beginning of the project, would be yet another oceanographic instrument for measuring conductivity, temperature, and depth. As I will be presenting in the following, this probably will not quite apply to this instrument. It's a bit unique, and especially the sensor which was developed for this application. Okay, so oceanographic probe for measuring conductivity and temperature and depth of seawater is, of course, one of the most prevalent instruments in the oceanography, and it's basically used to measure the salinity of seawater. And of course, we see currently with the ongoing climate changes, this is quite an important parameter to profile the movement of sea masses, assessment of flows, and so forth. So it's used basically to measure a profile of a body of water. So it can be actually put on a robot, an AUV, as it is in our case, which was tested then in Portugal. It can be either on a glider or a buoy or on a research vessel. So it can be towed, it can be seen, it can be put through the column of water either in the vertical way or in the horizontal way. So we can see the spatial variations in both directions. And of course it can be stationary, so we can also see the temporal variations of salinity at a certain depth. So this is perhaps one of the most interesting test cases on the estuaries of the rivers, where the ocean meets the river, so you can actually measure the salinity profile when the tide is changing. No? Okay, so basically how does it do this? When I said yet another one, how we started with this, I was developing the electronics, and my naive approach was to look at the existing solutions and probably use the shortest way to implement everything, and everybody will be happy. So I found this kit from Analog Devices, which is called CN0359, and we started this with as an orienting point for the electronics. So it's basically it's oriented towards measuring the conductance in the range from microsiemens to kilosiemens, and I said, okay, right, it surely can measure millisiemens, because the salinity of such salt water, our target salinity was somewhere in the range of millisiemens, 4 to 70, something like that. And of course, it features a temperature sensor, because this conductivity parameter is just bare conductivity. So this means in ohmic sense, which is not salinity. Salinity actually is both depth and temperature dependent. So it will need both temperature readout and a pressure readout. One of the things which was prerequisite for this project was to select a pressure sensor, which would be able to measure depths up to 2 kilometers. Okay. Then I checked, and actually let's say the Mediterranean is actually at its highest point, I don't know, probably more than 2 kilometers. So it is feasible to use such a depth sensor. And Danilo will probably confirm that the design of the casing for such a probe is quite challenging, yeah, for such depths. Yeah. Okay, so what can we use? We could basically use a temperature sensor. In its original design, Analog Devices provided us with the PT100 or PT1000 sensors. At this point, we said we can do better. So we used the titanium one, which has a bit of better response. So we used our titanium 2458 sensor, which was be faster and have a better sensitivity. This here is basically a block diagram of such a system. So those three sensors, as I presented them, will be then fed to this electronic model, and we'll go throughout the circuitry of this model. One of the things, one of the premises of this Nautilus project was to make this probe as cost efficient as possible. And the general idea was to use an Arduino model. So, of course, Arduino model cannot measure conductivities in range of, let's say, microsiemens and kilosiemens. It's such a vast span, you know. So for this range, you would have to use something better. And analog devices provided us with although old and slow and so forth processor, but it has integrated 24-bit ADCs with different features and so forth. So what we have used, this is this ADUCM controller, which provides signal conditioning for the electronics, which is then feeding the sensors. If we start with the conductivity sensor, so this is actually our added value, our scientific added value to this project. So this is our low-cost printed 4 electrodes, which is actually the essence of the conductivity sensor. So what you have here is our 4 electrodes. Here you can see you have 6 because you have also a temperature sensor inside. So 4 are allocated for the conductivity measurements, and I think the outer ones are for temperature. I think, yeah. So the inner 2, I think, they are for voltage. The outer 2 of the 4 are for the current excitation. And what you basically do is you put through the current and you measure a small voltage drop, as probably you always do with your instrument. However, those values are quite small or either quite large on the other end. So this technique would not be so useful. Instead, we use this synchronous modulation approach with a differential measurement, signal measurement path, and this then can be used to exploit those conductivity ranges. First thing is the excitation. So what you have to do with this synchronous modulation approach is basically to cancel out all the any residual voltages and so forth, which would be induced on the voltage measurement electrodes. So in this case, we have presented to the current current source, with a programmable amplitudes in a range of here you can set. For this range translates basically to the range of from 0 to 10 volts. Although in our case, this was provided by analog devices, but in our case, we have then narrowed this thing to, I don't know, several hundred millivolts, 1.6 volts, I think it's in final version. So as I said, from this vast range, we narrowed down the power consumption of the sensor. Right, so this actually what it does is it extends basically this voltage to positive and its negative counterpart. So actually what we will be doing on the next slide, we will be altering this voltage so to produce a square wave signal, 50-50 symmetry, with this thing here, which is the nemesis, our nemesis, so our switch, which is also a voltage dependent switch. So basically when you have a large power supply, it will act like it's drawn here, but the problem is that this is actually a transistor, so that it will add to the resistance which is here, and it's defining the transfer ratio of this voltage to the current. Yeah. So what you saw before can be then translated to the excitation current of milliamps. If you go to this R9 is 1 kilo. Some protection here on the left-hand side, and this goes then to the cell. So the current input electrode of the conductivity cell. Right. So this is the cell connector. So here, those 6 pins which I presented before. So this is the cell voltage, excitation voltage, and this thing is then the current is then fed through the sensor and output on the 6th electrode, transformed to the corresponding voltage. So this is the current to voltage converter. Especially you have to pay attention to this R26, which is quite an expensive resistor. It will basically transfer some nano amps to volts and so forth, using, of course, an additional amplification stage. So here you have two PGAs, two programmable gain amplifiers, which are able to extend this range, measurement range, in decades. So, and again, analog devices provided us with a range of those stages from 1, 10, 100, and to 1,000. As it has been proven, we don't need such a vast range. In our case, we just use 10 and 100. At least that has proven for a normal operation. Of course, if you go in one or other extreme, then you can detect the sensor fault. That's also another feature. Right, so then we have this voltage here. So current transformed to voltage and actual voltage differential measurement here from the sensor. And what you need to do is then to sample those two voltages synchronously in order to produce an accurate readout. So what it does, here is a simplified graph of how it works. This is the cell voltage. So excitation voltage in both extremes can be programmed. And then what is the point? The point of this synchronous modulation is to provide two controlling signals, PWM1 and PWM2, which actually then feeds such synchronous modulation stage. And of course you have low pass filtering and some buffering and so forth. So at this stage you will be producing a differential voltage, okay, filtered and a bit amplified to via those programmable gain generators. So this amplified voltage then is fed through a filter. This is a Butterworth second stage bandpass filter. So what we need here is to feed filtering voltages from both current and voltage inputs to produce then a differential output. Only one stage is shown here. Actually, there are 4 stages in parallel. So then this is differentially fed directly to the microcontroller. And okay, how does this measurement work? So if we know the actual settings from the programmable gain amplifier, in this case G1 and G2, then these differential measurements from voltages can be back translated using those resistors which you saw before to the conductivity. That's one thing. And of course, everything is ratiometric, so you don't need any ADC precision references. This is very important because as everything floats around with this seawater environment, you cannot have ADC, good ADC stability, and you cannot expect it, of course. So yeah, right. Okay, yeah. Accompanied by this conductivity measurement, you have to provide, of course, a special or better temperature measurement because you have to compensate this thing. And this thing varies quite a lot. So 1% to 3% per degree of centigrade. So if you don't provide an actual temperature measurement, you're just measuring conductivity. And of course, everything is a bit nonlinear. It's very well theoretically supported. So you have this set of equations which you can fulfill with those measurements. But in our case, we have a special opportunity to measure this temperature very accurately. In this case, you either can perform a 2 or 3 or a 4-wire measurement. So what you saw before, those 2 contacts which you saw from RTD on this 6-pin pin out from the conductivity sensor, the 2 are actually connected in a 4 connections setup. So Kelvin setup. So in this case, again, the entire thing is differentially connected. So this microprocessor also has a programmable current source. So you can provide an excitation current for the sensor, and basically you have one precision resistor, and you are measuring this Rx according to with this with this. So the ratio of R13 to Rx is basically measured quite precisely, as shown here. So, and also another feature, if you don't use, so if you use 2 or 3 wire connection, you can also detect the failure of one of the electrodes on those sensors. So there is also another thing, because this thing cannot be in buffered mode, so you have to offset the lower point. That's why this resistor is here. Okay. Pressure sensor, as we said at the beginning, we started with a sensor which was able to measure up to 2 kilometers, and we used an existing solution. We used the Keller sensor, pressure sensor, and this one is actually modeled here by those 4 resistors here. And actually, again, the microcontroller has additional differential inputs, so with the internal PGA. So what we need to do is just to put the 2 output sensor wires directly to the microcontroller and then set everything inside the microcontroller. So if we do this, then we are able to measure the voltage up to microvolt region, which can then bring us to, I don't know, several centimeters of resolution on a 2 kilometer range, quite nicely. Okay. Right, so this was our setup. Initial setups on the sensors were performed using 3 types of instruments. So one was the LCR meter, because actually when you're talking about conductivity and those 4 electrodes, you're not talking about resistance. You're talking about a combination of resistance and capacitance. So what you need to do is to use this LCR meter to assess the basic properties of the sensor. Then we have used, in our final stages, we have used our electronics. So this is this magic board which I've been presenting, connected to the PC, and then this is the reference sample with this EPI tube sample in it. And such a setup was used to obtain this. So this was the dots are the reference values of the certain salinity, different molarities here. And here you can see how good this thing will be corresponding to the measured values. So I think it's quite good. Okay, this is the long-term stability. So this was one of the problems, because here you can see the finished product when we selected the actual consistency of the sensor, because I wasn't speaking about the internal structure of the sensor, what materials were used. But here you can see that in the end we were using porous gold to be able to do those electrodes in a stable way, because otherwise we would get different things, so degradation and so forth. And this then again proved as a finished finished stable product. And also the electronics itself was also affecting the sensor stability, which I was not talking about currently. Here you can see what you can get from the temperature measurement. This is compared to now this is just the temperature coefficient of our resistor, and here I think you can see the comparative measurements with the PT100 sensor. So here you can see the actual deviation. So you can see 0.01 degrees of centigrade of resolution here. Okay, and then again, as I said, the probe can be lowered down in a vertical way. So this means that not only the sensor has to be precise, it also has to be fast. So if you will be using PT100 sensor in comparison to ours, you can see also from here that ours is a bit faster. So again, an improvement. So yeah, to present the end results, as I said, as I was bragging about, it has been quite a journey, because things are a bit different, you know, than with this analog devices kit, especially on its input stage, when we were designing this here. this here. So our modification to this sensor from the analog devices is this. But this here, this addition here, is basically making the sensor work. Because if you're using this analog devices kit, the electrodes get eaten away. Why? Because there are some chemical reactions which are originating from the input stages of the PGA. So if you are using this resistor here, you're balancing out this PGA stage, and you are annihilating the input current variation. So this is one of the things which were just so subtle results, you know, of this project, how we made it work, actually made it work. Yeah. And currently we are now in the process of transferring this to a third company, which will be actually producing those models, making them battery powered and logger operated and so forth. And hopefully we'll sell some sensors. Okay, thank you.
Yes, thank you, Matej.
Thank you
for the presentation of the
Sorry,
journey,
long presentation.
Development journey. So
yeah, it's a journey.
yes,
It's still a journey.
it's
Yeah, but I have a story.
question. Yes, Marco will join us.
Thank you for this presentation. And if I understood correctly, this input stage was causing some DC bias.
Yeah. This was
that
good.
was heating the electrodes.
This was good. Yeah, this was good. This is because, as I pointed out, this thing has a, let's say, an auto range, you know. So it sets both ranges from 1 to 1000. Huh? So if you see here, this thing can go from, let's say, volt range to microvolt or millivolt range, like this. And if you don't follow this with software, because you're actually doing this, you're changing it down and up and so forth, what you do is you're making things cook. Yeah, sorry, yeah.
And another question is just the measurement of the temperature.
Yes.
You use the DC current source.
Yes.
But you could use that because you had so
this one has
good A to D converter.
One thing is that, and also the current source itself is state of the art. Yeah.
Was that due to the self-heating of the sensor?
Yeah. This thing has programmable current source here. This EXC can be programmed in 10 microamp steps up to 600 microamps. So it can also be turned off. Mm-hmm. So this means that you will lower down this excitation current in order to reduce the self-heating. Can be done. In fact, we have optimized it to 100 or 200 microamps at the end. But as I said, it can be operated in pulse mode, so it doesn't affect the readout.
Okay, thanks. Anyone else wants to comment and ask the questions?
Sure.
So I'm actually wondering, so the conductivity that you measure with that method, this is conductivity is an integral parameter, so as if you would have an element with conductivity, but how do you translate this into the specific conductivity? I mean, do you account for the geometry properties of your electrodes somehow? Yes. Do you assume the transmission line behavior or something like that?
No, transmission line, no. But actually there is in this vast analysis, in this set of equations, there is a constant which is defined by geometry of the sensor, yeah. So, electrode pitch, length, and so forth, yeah.
Okay, thank you.
Maybe one more. How long the measurements take? I mean, one measurement.
Our Portugal friends have experienced this in our first step. Yeah, we got such erratic behavior because this thing doesn't work. So they plugged it in. It has a special command for setting this 15 volt power supply. And what they did is actually to use it as a switch, you know, so without any setup times and so forth. So actually this thing has a setup time, and we have tried to minimize it. We have minimized it to, I don't know, 20 seconds, something in that range. But then when it's powered and stabilized and so forth, so the measurement frequency, output frequency of this thing is about 1 hertz.
Okay. And how long do you want to have this sensor in the sea? For hours, weeks,
months,
years?
Months.
Okay, months.
Yeah, we're nearly not there yet, because in our current configuration, this thing is not battery powered, and even if it would be, it would still consume 50 milliamps with this 15-volt power supply on, which basically would take an enormous battery to feed. So this currently we're ongoing with the process of decreasing this power consumption. This is one thing, and also integrating it with a logger and the battery, so that it will be able to measure for months. But again, it's not feasible beyond months. It's probably not feasible because of biofouling. You have to be able to keep the electrodes clear, which is, I don't know, hard. Yeah, sure, everything's clear there, yeah? Nothing's there, so actually you can provide sterile conditions. Yeah.
Thank you.
Yeah, so.
So I would like to know about the selectivity of the electrodes and how does it affect if you use the sodium chloride or potassium chloride salts to the conductivity.
Okay, so if we go back to the sensor. So actually, I think it's so we have this those printed electrodes, and actually we have this epoxy coating, which is also a problem. Because there was this corrosion going underneath. And so in long-term stability, in laboratory conditions, we didn't have any problems with this. I think this is the correct way to say it. However, so far so good, let's put it this way. We'll see. Initial tests have proven that there's basically no effect on the corrosion of the electrodes. So we'll see how this performs in actual conditions.
The selectivity for different types of salts, they probably have different.
Yeah, what kind of salt would you like to have in salt water?
Chloride, potassium chloride.
Oh, actually, I don't think we tested this. No, we didn't test this. We expect salt to be in salt water. It's perhaps at Yokohama Harbor, a bit mercury and so forth.
Okay.
Okay.
Thank you, Matej.
Yeah.
Thank you.